Okay, this problem is actually pretty tricky for reasons I'll explain in a minute. It says the size of a bird population is modeled by the function p, that is a solution to the logistic differential equation dp dt equals this. Right away I notice that's not in the form we like, or at least the form that I teach my students. The form I teach my students is this one. And so if something isn't in this form, one way to kind of get around it is to try to make it look like this form. Because remember, that's the carrying capacity. So it's just kind of looking at us right away. Okay, so this isn't in that form, and maybe we can turn it into that form. T is measured in years for a positive or equal to 0 time value. And the initial population is that P of 0 is greater than 0. Okay, so positive initial population. Which of the following statements could be true? So this word could be true is actually essential in this problem. Let's work with our differential equation. I'm going to try to get it into the form we like and then see what we know about it. So right now it looks like this. So in order to make it look like the Kp m minus p, I might note that I want there to just be a p there. So how would I leave behind a p? Here I could factor out, well, first factor out a p, but also factor out a 1 over 2100. And if I do that, it leaves behind a p here. And the question is, what does it leave behind in the first term? Just a 700, right? You can take a look at that. Just distribute, and you'll see that you get p over 3. Okay, so the reason I like this form is because now I know my carrying capacity is 700. So let's sketch what this graph could look like for p. There's t. I know my carrying capacity now is 700. And I know these logistic differential equations have functions whose solutions tend to do this s thing, especially if your population is positive. So it's like some s curve. I'm going to erase it because we don't know, we don't know the details yet. It's going to be this s curve. So notice what that actually rules out is the number 1, right? Because the limit as t goes to infinity should be the carrying capacity, right? That's not equal, well, this is not equal to 700. So that's out. So I got to get rid of that answer choice. Okay, let me erase this for a second. What's tricky about this says the graph of p has an inflection point for t being greater than 0. Remember that the inflection point is going to happen at, so the inflection happens at half the carrying capacity. Okay, that occurs when p is equal to 350. So at 350, we have an inflection point. So is it possible that can happen when t is bigger than 0? Yeah, sure. My graph could look like the one I just did, where it's like that, and there's my inflection point. So 2 is possible, right? So that's out of there. The question is 3 also possible? And the thing is, it is. Let me draw this in green. That's asking if the maximum rate of change of p, that is another way of describing the inflection point, right? The maximum rate of change of the population is when the slope of this curve is biggest, which is the inflection point. Is it possible for that to happen right at t equals 0? Yeah, it's possible right at this moment, right? For your your logistic differential equation to begin basically at the inflection point. Okay, if we ignore the fact that t is greater than 0, and we just kind of but take a look at what a graph might look like. It could look like this, where yes, we're in negative time values, but my inflection point would happen right there. It is possible for your graph to start right at the inflection point, and in that case, that would make 3 true. Okay, so it's tricky, right? For a couple of reasons. One is we're not saying it's true. It's what could be true. And that sort of points out what could happen. So it could be the green, it could be the purple, and we don't know which one, but either of those could be true based on what we're given.